Cohesion is the property of like particles sticking together due to their mutual attraction, such as chemical bondings and intermolecular forces. Due to cohesion, a particle located away from the surface is pulled equally in every direction by neighboring particles, resulting in a net force of zero. The particles at the surface do not have the same particles on all sides of them. This creates some internal pressure and forces surface to contract to the minimum area. In terms of energy, a particle in contact with a neighbor has a lower energy than if it were alone. The interior particles have as many neighbors as they can possibly have, but the surface particles have less neighbors and therefore have higher energy. For the system to minimize its energy, the surface area must be minimized. Therefore, a free droplet of liquid naturally assumes a spherical shape, which has the minimum surface area for a given volume. Due to the tendency to minimize the surface area, there is a tangential force parallel to the surface of the liquid. This tangential force per unit length is generally referred to as the surface tension. For example, the rectangular frame is composed of 3 unmovable sides that form a U shape, and a 4th movable side that can slide. If a liquid surface stretches over the frame, its surface tension will pull the movable bar to reduce the area. The force is proportional to the length of the movable side. Thus, the ratio between them, i.e., the surface tension, depends only on the intrinsic properties of the liquid, such as composition, temperature, etc., not on its geometry. In terms of energy, if the surface area of the liquid increases, the force does work on the liquid. This means that increasing the surface area increases the energy of the liquid. The ratio of the change in the energy to the change in the surface area is called surface energy, which is equivalent to surface tension. Surface tension increases with the strength of the attraction between the particles. For example, in liquid mercury, the atoms are bounded with metallic bonding, which is one of the strongest attractions. As a result, liquid mercury has one of the highest surface tensions of all liquids. Water molecules are bounded with hydrogen bonding, which is the strongest intermolecular force. As a result, water has one of the highest surface tensions of all molecular liquids. Pentane molecules are bounded with London force, which is the weakest intermolecular force. As a result, pentane has very low surface tension. The Laplace pressure is the pressure difference between the inside and the outside of a curved surface, which is caused by surface tension. Consider a spherical droplet. The upper hemisphere is pulled downward by the surface tension, while it is also pushed upward by the Laplace pressure. The droplet is static if the two forces balance each other. Thus, the Laplace pressure can be calculated by Young-Laplace equation. According to the equation, smaller droplet tends to have higher Laplace pressure. Adhesion is the tendency of dissimilar particles to cling to one another. The balance between the cohesion of the liquid and its adhesion to a solid surface determines the degree of wetting, the contact angle, and the shape of meniscus. Wetting is the ability of a liquid to maintain contact with a solid surface. The contact angle is the angle between a liquid surface and a solid surface where they meet. As the tendency of a drop to spread out over a flat, solid surface increases, the contact angle decreases. Thus, the contact angle provides an inverse measure of wettability. A contact angle less than 90 degrees usually indicates that wetting of the surface is very favorable, and the fluid will spread over a large area of the surface. Contact angles greater than 90 degrees, high contact angle, generally mean that wetting of the surface is unfavorable, so the fluid will minimize contact with the surface and form a compact liquid droplet. For water, a wettable surface may also be termed hydrophilic and a non-wettable surface hydrophobic. Superhydrophobic surfaces have contact angles greater than 150 degrees, showing almost no contact between the liquid drop and the surface. This is sometimes referred to as the lotus effect. At the line of contact where 3 phases meet, the net force per unit length acting along the boundary line between the 3 phases must be zero. The equilibrium of net force in the direction along the solid surface is the Young equation, which relates the contact angle to the interfacial energies between the three phases. The interfacial energy between a gas and condensed phase is approximately the surface tension of the condensed phase, because there is nearly no gas particle in contact with the condensed phase. A useful parameter for gauging wetting is the separation work, which is the opposite of solid-liquid adhesion energy per unit area in gas. Then, the contact angle can also be related to the surface tension of the liquid and the separation work by Young-Dupré equation. Young-Dupré equation can be used to calculate the interfacial energy. For example, mercury has very high surface tension due to strong metallic bonding. On the other hand, it has very low adhesion with glass. As a result, the contact angle between mercury and glass is about 140 degrees. The surface tension of the mercury acts over its entire surface area, including where it is in contact with the glass. Pouring mercury onto a horizontal flat glass results in a puddle. The liquid flattens out because that brings as much of the mercury to as low level as possible to reduce gravitational potential energy. However, the surface tension, at the same time, reduces the total surface area to reduce the total surface energy. The result of the compromise is a puddle of a nearly fixed thickness. The same surface tension demonstration can be done with water, but only on a superhydrophobic substance which water does not adhere. Polytetrafluoroethylene, PTFE, is such a substance. Water poured onto a horizontal flat PTFE surface will behave similarly to the mercury poured onto glass. For example, water striders use the high surface tension of water and their hydrophobic legs to help them stay above water. The legs of a water strider are long and slender, allowing the weight of the water strider body to be distributed over a long solid-liquid gas interface. The Young equation also predicts that if a liquid has very low surface tension, or the liquid and surface have very high adhesion, the contact angle is 0 degrees. The liquid will spread out into a micro-thin layer over the surface. Such a surface is said to be fully wettable by the liquid. For example, diethyl ether has very low surface tension, its contact angle with glass is nearly 0 degrees. Water, in despite of a relatively high surface tension, has strong adhesion with clean glass. So, the water-glass contact angle is also 0 degrees. Generally speaking, liquid and solid with similar polarities wet well because their surface tensions are similar, and the interfacial energy is small. The wettability is responsible for capillary action. For example, when a vertical glass tube is partially immersed in mercury, the mercury level at the center of the tube is higher than at the edges, making a convex meniscus. The center of mass of the entire column of mercury would be slightly lower if the top surface of the mercury were flat. But the convex top gives slightly less surface area of mercury to minimize the total potential energy. If a tube is sufficiently narrow, the mercury level inside the tube is also lower than outside the tube to reduce the surface area of mercury to minimize the total potential energy. If the liquid is water, the situation would be very different. Since water aggressively adheres to glass, increasing the surface area of water where it is in contact with glass reduces the total surface energy. As a result, the water meniscus in glass tube is concave, and water level inside the narrow tube is higher than at the outside the tube. The gravitational force of liquid in a tube is balanced by the surface tension. The height of the liquid is given by Jurgen's law. According to Jurgen's law, the height of liquid in a capillary tube is inversely proportional to the tube's diameter. Surfactants are chemical compounds that decrease the surface tension or interfacial energy. The word surfactant is a blend of surface active agent. Surfactants are usually organic compounds that are akin to amphiphilic, which means that this molecule, being its double agent, each contains a hydrophilic group, the head, and a hydrophobic group, the tail. As a result, a surfactant contains both a water-soluble component and a water-insoluble component. For example, sodium dodecyl sulfate is a widely used surfactant. It has a hydrophilic sulfate head and a hydrophobic 12-carbon dodecyl tail. Surfactants diffuse in water and get adsorbed at interfaces between water and air, or a hydrophobic surface. They play an important role in wetting solution. Due to decreased liquid surface tension and interfacial energy between the liquid and solid surface, the contact angle is reduced, meaning that the surface is more wettable. For example, adding surfactants to water can remove the lotus effect of wheat leaves. In the bulk aqueous phase, surfactants form aggregates called micelles, where the hydrophobic tails form the core, and the hydrophilic heads are in contact with the surrounding water. The shape of the micelles can be spherical, cylindrical, or bilayer. Surfactants can act as emulsifiers. An emulsion is a mixture of two or more liquids that are normally immiscible. Emulsifying occurs because the insoluble species can be incorporated into the micelle core, while the micelle itself is stabilized in water by the virtue of the hydrophilic head. The most common example of emulsifiers are detergents, which clean poorly soluble lipophilic material, such as oils, that cannot be removed by water alone. Detergents clean also by lowering the surface tension of water, making it easier to remove material from a surface.